now.
I think the United States might.
Today, Matt will give his last, fifth lecture and start the morning session. Just a reminder, today is an easier day, no discussion session at the end, so you can start relaxing earlier. Okay, so let's give Matt the opportunity for the last lecture.
Okay, great. So I wanted to backfill a couple of things from yesterday. I don't remember if I said this or not, but I should say it. This business about the computing this by having alpha sheets and a branch cut is called the replica trick. And in general, people use the term to denote the whole method of computing S by computing the Rennies and then taking the limit alpha to 1. So there are two steps here which are logically independent, but in practice they tend to go together. One step is how you compute the Rennies by replicating the Euclidean manifold defining your state. And the other is, the second step is then having computed the Rennies, taking the limit alpha 1. And I guess this one is called the replica trick, but people tend to use the term for both together. Now, Miriam just asked me an excellent question, which may have also confused some of you. So what I said is that we're going to compute this for alpha equals 2, 3, etc., and then take the limit alpha to 1. Now, why don't we just go ahead and take the limit alpha to 1 first before doing all that work of computing the partition function on some complicated manifold? I mean, after all, what's the problem? Taking alpha to 1 is very easy. Let's get rid of this stuff, okay? And then it's just the partition function you had originally. But that misses the point, because actually the Rennie, recall, is defined in this way. And what happens when I take alpha to 1 is that this, if I just take alpha to 1 on this, I get 1 because rho A is a density matrix, normalized. So this is 0. The denominator is also 0. So what you're really interested in is not the limit as alpha goes to 1 of this quantity, which is 1 by definition, but the limit as alpha goes to 1 of the derivative with respect to alpha of this quantity. And so the tricky part here is, the real question we're asking is, if I have alpha copies, what is the first derivative with respect to alpha at alpha equals 1 of this replicated partition function? Which is not at all obvious if you just first fix alpha to 1. If you first fix alpha to 1, you're not going to know what that first derivative is with respect to alpha. Okay, so that's why we have to do all this work of computing it for alpha equals 2, 3, 4, fitting to a function of alpha, an analytic function, then take alpha to 1. Okay? So I hope that's a little bit clearer. So there's quite a bit of content. Yeah?
The twisted state actually play not your role
Yeah.
because of this derivative.
Yeah, exactly. So you have this very subtle thing, which we're not used to doing necessarily in CFT, of taking a derivative with respect to the parameter defining the twisted state, the twisted sector operator. And if we knew better how to think about that, it would actually be quite helpful. I'm going to give an example in a few minutes where our sort of lack of understanding is hampering us. Yeah?
Isn't it going to be hard to associate any physical conclusions from, like, approximate because we'll have, like, things that either have off, like, break, that, they'll be
Well, are you referring to working in some kind of saddle point limit or something like that?
How else do you do this when you can't solve it?
Well, so I did it for CFT.
No, that's higher.
Yeah. So in a general quantum field theory, it's very hard to compute this, and then you resort to various tricks. So that those tricks could be numerics. So this is even aside from the. I mean, again, there are two steps, and the example I gave was, as usual, when we learn physics, I first gave the easy case, which, as usual, when we learn physics, is totally non-representative, right? It's like learning particle in a box in quantum mechanics and the hydrogen atom, and then you get the impression that it's easy to solve quantum mechanics problems, but in fact, those are the only, and harmonic oscillator, those are the only three you can solve, right? And the whole rest of quantum mechanics is approximation methods. Okay, so there's a whole, I could give many lectures on approximation methods or tricks, such as saddle point, various numerical methods, various kinds of perturbation theory, expansions for computing this, and then there's this step. Okay, so actually, let me not launch into that because there isn't any one. There are many methods. They tend to be complicated, and it would take me a long time to explain any one of them. And they all have their caveats and their pluses and minuses and so on. So I'm sorry. I'm just going to dodge that. Basically, I'm just going to dodge that question. But of course, I mean, there are many valid questions you can ask. For example, given an approximation scheme for this, can you then take the approximate value of this, fit it to something, and get something meaningful here? I mean, that's a very valid question, and particularly if you're using something like a saddle point approximation. Yeah.
Well, yeah, but I mean, sure, but that's true of like everything we calculate. I mean, usually processing things that are actually like non-perturbative or something that are vital for the underlying physics. But when we do the approximation schemes, we usually learn something about the underlying physics. My concern here is the auxiliary nature of the replica. That it's just all we can do is black box to an answer, some number, and then try to interpret that. We can't actually use, we don't gain any insights from doing the approximation scheme necessarily because of the fact that we have these auxiliary.
Well, I mean, if this is a physically meaningful quantity.
The answer, yes.
No, the intermediate step. The Renyi entropy is a physically meaningful quantity from which you can extract useful information and which you can check against your intuition and your physical understanding of the system. So it's not, this is, I mean, I'm not sure I want to describe this as a black box or some kind of intermediate step that has no physical meaning. The Renyi entropy has a clear physical meaning. It's a moment of the distribution of eigenvalues of the density matrix, and you can check your answer against your physical intuition. You can, you can, even if you can't do this step, you already have learned something about the system. So, not that there aren't subtleties, and as I said, there are especially subtleties if we're doing the saddle point approximation. There are big subtleties there. But I don't want to just say that we only care about this and that this is just some kind of black box. Okay, so let me proceed, get back to the thread that we were following at the end of the last lecture, where I was going to higher dimensions. And again, I mean, there's a lot of different results, and I'm just kind of distilling out the punchiest things that have been figured out, so the cleanest results. So one very clean result is this calculation of the entanglement entropy for a disk in a 3D CFT. This calculation, by the way, is Cassini, Huerta, and Myers from 2012, I think. And the conclusion there is twofold. First of all, that there's a universal finite contribution which corrects the disk, which corrects the area law piece, the non-universal area law piece, you can show that it has to be negative, and furthermore, it's basically equal, and I think last time I forgot to write a log, to the S3 partition function, so actually the universal part of, so both of these quantities are kind of dirty. The three-sphere partition function has some divergent crap. The entanglement entry has some divergent crap, and you can't really compare those. But the universal finite parts on both sides are equal. Okay, and so this is something you can compute in a CFT in various ways. This is something you can compute, so this is already interesting because this quantity characterizes, it's in some sense analogous to the central charge of a 2D CFT. But it's a little bit weirder than that because, for example, if you have a topological theory, then you get a non-zero F, whereas in 2D, a topological sector doesn't contribute to the central charge. Now, it gets even more interesting if you ask about non-CFTs. So for a general 3D theory, well, first of all, let's say it's an RG flow that has nice, well-defined fixed points, UV and IR fixed points. So we can define this quantity, this F function, so regardless, we're going to have an area law term. So we're going to have a term like this in any quantum field theory if we're talking about the disk entanglement entropy. So S of A equals the disk entanglement entropy, which is a function of R. And now we want to strip off the divergent part. So the divergent part is proportional to R. And so if I write this, then it'll cancel between these two terms. So any term that's linear in R cancels. And then I get something else, which is some function of R. Okay? Now, if S happens to take this form, which it does at the fixed points, then I'm just left with F. Okay? So, well, if I just plug that in, so I'm assuming that for R very small, it takes this form for some F. And then I plug it in, and I'm left with F, right? And at very large distances, again, it'll take this form, and this coefficient will be totally different. It will have accumulated all kinds of stuff in between. So the coefficient of the area law piece is going to be totally different in the UV and the IR. So, but either way, it's stripped off. And so we have this. And this is called the renormalized entanglement entropy. So it was defined by Liu and Meze in, I think, 2000. I might be getting the years wrong. I mean, first you have Cassini, Huerta, and Myers, I think in 12. And then also in 12, you have Liu and Meze defining this function and suggesting that it might be monotonically decreasing. And then you have the proof by Cassini and Huerta that strong subadditivity implies that F prime of R is indeed non-positive. And so you have the same picture of a function which decreases from the UV to the IR. And so in particular, you have this very important consequence. So this is very closely analogous to the Zamolodchikov-C theorem. But the difference is that in 3D, we didn't have Zamolodchikov. So in 3D, we first had Zamolodchikov, who used local operators, namely the stress tensor, and properties of their correlation functions to deduce the C theorem. And then later, Cassini and Huerta came along and reproved it using entanglement entropy. So they proved something we already knew. But in 3D, you don't have that first step because, for example, if you have a topological theory, you don't have local operators. So you're not going to be able to detect F by computing correlation functions of local operators. Okay? You can compute F by looking at the partition function on the 3-sphere. So it's an inherently non-local quantity. Okay? So now, Cassini and Huerta's proof of the F theorem tells you something you didn't know before about three-dimensional theories. What, am I too low? There was a question, yes. But those are equivalent. So you can do two different things. You can hold your UV definition of your theory, which means I hold fixed like my lattice or my whatever my regulator is. I hold that fixed. This would be like the condensed matter point of view. Like there's an underlying atomic lattice, okay? And now I'm just zooming out and looking at this system at longer and longer distances. So if I want to characterize this theory, how it looks at some distance, I look at a two-point function at that separation, or I look at an entanglement entropy of a disk of that size. So I look at some physical quantity whose definition depends on some size r, and then I adjust r to be small and then to be large. Or if you want to think about it from a field theorist point of view, I fix the size at which I'm looking at the theory, and I vary the cutoff. Let's make the cutoff a distance, so an epsilon, and I take epsilon to 0, or I change the value of epsilon, and that would. But these are equivalent. So it's just, when you zoom out, it's the same as shrinking your system. Okay? Right. So in this story, I have a fixed theory, meaning the full definition of the theory, including any cutoffs, any regulators, are fixed as I vary r and plot this function. Okay? That doesn't mean that in this expression, in the infrared limit, this epsilon equals my actual cutoff, because I will have accumulated contributions from everything going on in between. So the coefficient of r in the infrared limit will not be the same as the coefficient of r in the ultraviolet. Yeah?
I don't think it's proven yet that the f of r is
right. So this is a little misleading in that you can have a derivative. It can look like this. Yeah, that's true. So how did they prove this theorem? They were interested. It's morally similar to the proof we had before, but now we have disks, and we're using relativity. And in fact, I should have said that. It's, of course, again, Lorentz symmetry and strong subadditivity. Both are necessary. So you take these disks and you boost them in all these different ways, and then you apply strong subadditivity instead of just once, many, many times. And you just keep track of all these different contributions. And what happens, so you have these boosted disks, and you look at their unions and intersections, and you do a few lines of algebra. It's the kind of thing that after you've seen it, it's like, oh yeah, I should have thought of that, but but you didn't think of it. They thought of it. Okay. So what about higher dimensions? But let me just say, this F theorem is the only constraint we have on 3D RG flows. Okay, so it's really genuinely new information, and it's quite fascinating because the F that enters, unlike what we're used to in 2-dimension, does not reflect the number of local degrees of freedom, because even in a topological theory, even topological sectors contribute to F. And I don't think we really understand very well what's going on there. Okay, in 4D, so for a 4D CFT, by very similar reasoning, you get the following expression. So now we have logs. So this is for a ball. Now we pick up logs, so that the area law divergence looks like this. And there's no linear term, and there's no universal constant term. And this is the A-Weyl anomaly. It's not A-Weyl, it's the A-Weyl anomaly coefficient. What? Huh? This is a 4. Yep. So again, you can define, well, so by sort of similar, actually, let me back up a second. So after Zamolodchikov proved his theorem in 2D, Carty conjectured this statement. In 4D, you have two Weyl anomaly coefficients. One is called A and the other is called C. They multiply different curvature invariants. Carty conjectured that A is the one that decreases along RG flows. And then this was proven using sort of, very roughly by analogy with Zamolodchikov's proof of the C theorem, using correlation functions of the stress tensor and unitarity by Komagratsky and Schwimmer a few years ago. But they had to, instead of it being 2-point functions of the stress tensor, using 4-point functions of the stress tensors. Much more complicated proof. This was proven just a few days ago using the ball entanglement entropy and strong subadditivity by Cassini, Teste, and Toroba. So, and this is the A theorem. And so now we have entanglement entropy-based proofs of, so again, the terminology for the theorems is in 2D, it's called C. In 3D, it's called F. And in 4D, it's called A. And I don't know what it's going to be called in 5D. So we don't have any theorems above 4D. We have conjectures which are not really on super firm footing for higher dimensions. Yeah?
If you try to imitate what you did on 4, for example, you get that.
Yeah. No, this is, so remember how I,
Even dimensions,
yeah.
this local way in terms of correlation. And
Yeah. Yeah.
the concept.
Yeah, I mean, so if you remember a few days ago, I didn't calculate the 2D version, the C over 3 log L over epsilon using the sphere. I said I could have done it using the Weyl anomaly. And so again, just from the 4-sphere partition function, you can get this. And it comes from the Weyl anomaly. And you only pick up A because the curvature invariant that multiplies C in 4D vanishes on the 4-sphere, on the round 4-sphere. And so that's one way of understanding why you only pick up A. So indeed, this relation here comes precisely from considering the four-sphere partition function. Yeah, yeah.
So what is the obstruction to the proof you described where you have a ball and then you that's just super.
Oh no, it really is. And I didn't get into the details, but essentially, I mean, there was like a 5-year gap between these two proofs, and when you look at unions and intersections of boosted balls, you have corners, and the corners lie on null planes. And you have to argue that those corners do not give you extra contributions. And actually, or it's a little worse than that. So in 3D, you argue that they don't give an extra contribution. In 4D, you know that they do. And you have to, then what you have to argue is that they give the same contribution in the UV and the IR. And it becomes much more subtle, actually. And then you could say, well, having taken care of that subtlety, now can we just extend it to higher dimensions? But the tricky thing is that essentially, if you want to get rid of this term, you're talking about taking a second derivative of this. And strong subadditivity, as I showed you, is a constraint on the second derivative. It's a concavity, essentially. But in higher dimensions, let's say in 5D, you're going to have r over epsilon cubed. So you would need a constraint on the third, to get rid of that, you need a constraint on the third derivative. Strong subadditivity doesn't tell you anything a priori about the third derivative. Okay, and so that's where, now maybe in 5 years, Cassini and collaborators are going to prove, every time they write a paper on this, I mean, this is absurd, and every 5 years they prove it for higher dimensions, and every time at the end of the paper they explain why they can't use the technique to prove it for the next one. And they give a very good and convincing reason why they'll never be able to prove it for the next one. And so, you know, or maybe one of you will do it. So let's not wait 5 years. Just go ahead and do it now.
So strong subadditivity is telling us 4 dimensions is special.
Yeah, a priori, it looks like that. And so it's possible that there are not such theorems, or that you can't prove such theorems in higher dimensions.
Now, there's another question over here.
Oh, yeah. In 2D, where strong subadditivity appears is that it says that the mixed second derivative with respect to the two endpoints is negative.
So what I'm confused is,
Yeah.
You have a quantity which increases if you go from UV to IR. But the quantity, the way that it appears in the entanglement entropy is that the entanglement entropy increases, but it's very difficult to decrease with
You're worried about this, that this is a minus?
Side, but it's the plus side.
Well, actually, even in 3D, it's yeah, in 2D, yeah, good. This is not the same in the UV and the IR. Okay, so it's not true that this whole thing is a decreasing function. In fact, well, even if this was the same, it wouldn't be a decreasing function because, of course, this is increasing. Okay, so you know, it's some kind of in some sense, there's a deficit in the entanglement entropy. There's a very small, there's the area law part, and then there's a very small deficit. Okay, and that deficit, I guess, decreases from the UV to the IR. I don't really know how to, you know, what intuition to give to the sign of the change in the deficit.
Yeah, but what I'm confused is the sign is different.
Yeah.
Is 2D or 3D.
Yeah.
The constraint equation is different, right? The inequality in different dimensions, because there is a d minus 2 or 1 factor and we changes sign when you go from d to 2 to 4.
Yeah. Yeah. I don't have a snappy answer. you know, you're doing, in higher dimensions, you're doing more subtractions to get rid of these. Like if you write down an analog of that in 4D, you have something that involves second derivatives, and it just, I don't know. So you just end up doing more subtractions, and you end up with a different sign. I think there's probably a nice answer to your question. I think I understand your question now, but I don't have a snappy answer. Okay. So the last thing I want to talk about in terms of field theory is the mutual information. And there have already been quite a few questions on this. So here we can consider some A and B separated, and then we expect this quantity because if they're separated, so they have no common boundary, and because the divergence stuff is all integrals of local invariance along the boundaries, that'll cancel in the mutual information, and so this will be finite and meaningful, and it quantifies the amount of correlation. And so it's interesting to try to calculate it. Let's just consider 2Ds, in fact 2D CFTs, to give ourselves as much of an advantage as possible. And it's actually surprisingly hard to calculate this. So if you do the replica trick, then you end up with, so the replica trick here instructs you to compute the partition function on a genus alpha minus 1 Riemann surface. And so as soon as you go above, well, like already at 2, you have to do a torus partition function. And you know that unlike the sphere partition function, which depends only on the central charge, the torus partition function already depends on the full operator spectrum. And the, let's say, genus 2 partition function depends not just on the spectrum, but also on the 3-point functions. And so this is going to depend in a much more, you're going to expect that this mutual information is going to depend in a much more complicated way on the CFT than just on its central charge. Or at least that would be, unless something amazing happens and the alpha goes to one limit, which I can tell you doesn't, you expect this to be much more sensitive to the details of your CFT, and also much harder to compute. Now, another way to say it is that you have to compute a 4-point function of twist operators in some orbifold, and 4-point functions are much more complicated than 2-point functions, obviously. And then you can bring to bear a lot of CFT technology to do that, which I'm not going to go into, but let me just give an example where we know the answer. So I'll call these endpoints, you probably can't read that, A1, A2, B1, and B2. So this has been computed for a free massless Dirac fermion by Cassini, Fosco, and Huerta. And they get something which is a function of the cross ratio. So I want to say a few things. So first of all, this is a rather remarkable, the calculation itself is rather remarkable. It can be done by the replica trick, but that's not how they did it. They actually did it, and this is the only case I know where this has ever been done in any field theory. They actually wrote down in a basis the reduced density matrix. not in some formal path integral sense, but like matrix, all the matrix elements of the reduced density matrix in some specific basis are actually written down, and from that they actually computed the entropy. This is also, probably not coincidentally, the only mutual information that we know exactly in any field theory, in any number of dimensions, not counting topological field theories where the mutual information vanishes. Now you might say, oh, come on, like how about a free boson? And so, you know, no problem. I'm going to sit down and do it for a free boson. Because after all, for a free boson, you can look up the partition functions on arbitrary Riemann surfaces. They're closed form formulas for the partition function as a function of the moduli for an arbitrary Riemann surface. And therefore, we know actually all of the Rennies in closed form. But they're just complicated. And they're complicated enough as functions of alpha that we don't know how to analytically continue to continuous alpha and then take the limit alpha to 1. So we still don't know for a free boson the mutual information in closed form. Okay. Nonetheless, this thing, which I should actually plot, has a number of features that are common so qualitative features that are common to any 2D CFT. So the first is that it's finite, and I argued why before, and that implies that means that it's independent of epsilon, and that means that it's conformally invariant. And that means that it's a function of the cross ratio of the 4 points. It is non-zero because otherwise, by that inequality I gave before, when you have zero, or you don't even need that inequality, but when the mutual information vanishes, the density matrix factorizes, and if the density matrix factorizes, all the correlators vanish, and they don't. In any CFT, we know that there are non-zero 2-point functions, obviously. By strong subadditivity, it increases. So remember, strong subadditivity tells you that the mutual information is monotonically increasing when you adjoin something. So if I add C over here, so I increase the size of one interval, keeping their separation in the other interval fixed. So that means, in turn, so what I'm saying is that holding A1, A2, and B1 fixed, it's an increasing function of B2. And that means that it's a decreasing function using the fact that it's a function of the cross ratio. It decreases with the separation, which also makes sense, right? The amount of correlation should go down as I increase the separation, fixing the two sizes. That's very intuitive. And if you look at this, it goes to infinity. So let me call this separation S, as S goes to 0, and it goes to 0 as S goes to infinity. So you can check that those hold for this particular function. And let me just plot it. Well, it's some exciting function that looks like this. And furthermore, how does it go to 0? You can check the power of S. And it goes like S to the minus 4 delta, where this is the dimension of the lightest operator, lightest non-unit operator, which in this case is a half. Okay, and these are all, so you can prove that all of these hold. For example, you can, by studying the behavior of the 4-point function of twist operators, you can basically apply the replica trick in the limit of large separations and do the analytic continuation in alpha, and you will pick this up. Yeah. I mean, I don't think they're that, it's just some decreasing function. You know the power law at infinity. Probably with some... Yeah. Yeah, because it's finite, because the divergences are localized on the... So that what I'm saying is that...
It depends on the cross ratio. It should constrain it a little.
Yeah, of course. So it's one real function of one variable. Okay? Right? I mean... Yeah, it's... wait, what was your last phrase?
If I was to consider like
oh, I see. Complex analytic. I think we expect it to be. So the 4-point function. So for fixed alpha, it's certainly analytic because it's a 4-point function. Then, of course, you could ask whether when you take the limit alpha goes to 1, in principle, the limit of a family of analytic functions doesn't have to be analytic, but we sort of expect it to be analytic. Well, I mean, analytic on some, so it diverges at 0. Yeah, I mean, there's some, so it's holomorphic on some domain. Yeah. That's what I meant. It's not entire. Okay. Yeah.
So where is the CFT data in that formula?
Where is the CF? Well, this is for a particular example. I mean, so I'm not sure what you mean. Yeah. So in this case, delta is a half. And then if you expand this out, so fix B2 minus B1 and A2 minus A1 and let S be, so let me write this equals B1 minus A2. And then expand it out for large S, you will find that it goes like 1 over S squared. Yeah, we're going to see how far we're going to get into. I have a half an hour left, so let's see how far I get into holographic things. Okay. Okay, and that is where I'm going to end my discussion of entanglement entropy in field theory. And there's far more things I didn't say than that I did, and I listed some finite list of topics I did not discuss in the notes. But I want to move on to holographic theories. Okay. So, yeah. No, this you can show in general. Right, so what you do is you can you apply the replica trick in a general theory, and before taking alpha to 1, you assume S is large, and then it sort of simplifies, and then you get a relatively simple formula on which you can take alpha to 1, and you get this. And in fact, I think you can say what this coefficient is. I don't remember. Yeah, no, I think this coefficient is basically up to some halves or whatever, the number of operators that have this dimension. Yeah. Yeah.
Actually, just use OP of the operators.
Yeah.
But if you get the twist operator, twist operator with the lattice operator, it's bad.
No, because the twist operators, well, yeah, I mean, right. I mean, the twist operators kind of see everything. They're a little bit like the stress tensor. They basically are sensitive to all of the other operators. So there's no, in other words, the 3-point function of twist, anti-twist, arbitrary other operators is determined entirely by the scaling dimension of that other operator. No, the slower. Is this another 4 1/over contribution confusion? Is that better? That's a 4. It's terrible. I had a professor in college who was from Russia, and we could not read his handwriting or know whether he wrote, had written a nu or a 4 on the board. And he said, I won't make you suffer with my fake Russian accent, but when we pestered him about it, he said, in Russia we have a saying, in Moscow there are no street signs. And the reason is, if you don't know what street you're on, what are you doing there? That was his answer. Okay, so it's very hard to compute entanglement entropies in field theories, except, strangely enough, in ones that have a lot of degrees of freedom and are at strong coupling. And in particular, if they have a holographic description. Okay, so where, like so many things, as Oliver has emphasized in his lectures, it becomes suddenly tractable because it turns into a classical problem. And this was a great discovery by Ryu and Takeyanagi. And I'm going to try to motivate it by talking a little bit about the thermofield double of a thermal state. Okay, that was my intro. The thermal state on S1, thermal state on SD minus 1, if we're above the Hawking-Page transition, is described holographically by a black hole. So, I should say above Hawking-Page transition. Okay, which looks like this. Some ADS Schwarzschild black hole, which has a horizon. Okay, this is our horizon. This is what a time slice looks like. And this is the boundary. And the thermofield double is described by, as I mentioned before, the maximally extended two-sided black hole. So this is the purification And so now we have an A and a B. Okay. And furthermore, well, what I should have said before, but anyway, the thermal entropy, which is now the entropy of A, I'll just go straight to that, is given by the Bekenstein-Hawking entropy. This is a black hole. This is Bekenstein-Hawking. Plus order 1 corrections, where the Bekenstein-Hawking entropy is the 1 over 4. This is a 4 G Newton times the area of the horizon, as you all know, which is itself order in field theory units, order n squared, or order c. So if you're doing a Yang-Mills theory in 4 dimensions, it's order n squared. If you're doing a conformal field theory in 2 dimensions, it's order c. And I'm going to ignore these for a little bit because there's such a big parametric difference between these two terms. Okay. So in this case, we actually know the entanglement entropy sort of by construction. The entanglement entropy is the area of this bulk surface which lies between A and B. And what is special about this surface? Well, of course, it's an event horizon. It's very special. We have tons of symmetry. You could say it's the fixed point of the Z2 that flips these. There's a larger symmetry in space-time. This thing is actually the bifurcate horizon in space-time. So the Penrose diagram is like this. And we have a bifurcate killing horizon. This is, let me make it orange, fixed point of some isometry group. So it's special in a lot of ways. And so if you wanted to generalize this formula and say, let's say I just have a general background and a general region A, is there going to be some formula for the entanglement entropy? And you might not know, okay, because you want to generalize this formula, but of course here the horizon was picked out by all of these different symmetry-dependent considerations. But if you're very brave and you just say, well, is there something about the horizon that doesn't depend on it being the fixed point of all these symmetries, you might notice that on this constant time slice, it's the minimal surface. And in the space-time, it's an extremal surface. In particular, it's the minimal surface that sits between A and B. Okay? So this is essentially the bold guess that Ryu and Takeyanagi made. Well, the generalization that they considered did use some symmetry, so they assumed a static background. This is static with respect to some funny killing vector that goes different directions in the future and the past. Oh, let me actually say one other thing first before I get to Ryu Takeyanagi. There's something quite fascinating about what happened when we did the Thermofield double, which is before we started with a space-time, which is basically the external part, the exterior of this exterior region of this black hole. And then when we purified and we said that now the entanglement between A and B is related to this Einstein-Rosen bridge, we got a whole new part of the space-time. So we suddenly, so if you start in an unentangled state between A and B, let's say, for example, you start in a state below the Hawking-Page transition, then you'll just have an A, and you can go ahead and calculate the thermofield double of that, and it'll be just 2 copies of ADS. Below the Hawking page transition, you just have ADS with a thermal gas of gravitons. So you just have 2 copies of that. And the amount of entanglement is the entropy of either side, which is order 1. Increase the temperature past the Hawking page transition, and now you have order n squared entanglement, and that is reflected in the geometry by the growth of this bridge which connects them. So the bridge seems to represent the entanglement, and not only did you acquire a bridge, you acquired these whole parts of the space-time that have no analogs below the Hawking page transition, where you have only order 1 amount of entanglement. So there's this idea that somehow space-time emerges from entanglement that you get by looking at examples like this and other examples where by tuning the amount of entanglement, you change the amount of space-time. Space-time kind of appears when you have more entanglement. Okay, so this point of view is advocated especially by Mark van Ramsdonk and has led to a whole line of research, which is closely connected to Ryu Takenagi. But let's ask how we can generalize this formula to a more general case. And A is lying on a constant time slice. Where this M is the minimal surface in the bulk that lies between A and A complement. So let me draw a picture. So I'm on a constant time slice, and I have some A, and I have some bulk. So this is what Oliver was calling R. Goes to infinity here. And now I look for the minimal surface in the bulk. So here's A complement. And what does it mean between A and A complement? I mean that it sort of separates the bulk into 2 parts, one of which is bounded by A and the other is bounded by A complement. So you have some surface which separates the bulk into 2 parts. And moreover, it's the minimal surface that separates the bulk into those 2 parts bounded respectively by A and A complement. Okay, so this can be made more precise, not somewhat, or at least, if not more precise, at least it can be made to sound fancier, which is also important. We would say that M of A is homologous to A, which means there exists a bulk region, spatial region, R of A, whose boundary is M of A union A. So here's my R of A, and the boundary of R of A has 2 components, M and A. Okay, so this is the celebrated RT formula, and don't forget that there's secretly order 1 corrections to this. Okay? Now, in the more general case, when we don't have this, then there's a generalization of RT by Hubini, Rangamani, and Takeyanagi called HRT formula, which basically says that this is the minimal extremal surface. So HRT says where the minimal extremal surface, meaning that a surface with vanishing trace of the extrinsic curvature, or if you put it a little more geometrically, it's an extremum of the area function. The reason you don't, in space-time, you can't talk about minimal surfaces is that you can always take any surface and jiggle it up and down in the time direction to reduce its area. So there's no notion of a minimal surface in a Lorentzian space-time. But so when you're doing HRT, then you're looking at codimension 2 surfaces, space-like surfaces in the full space-time. When you're doing RT, you've simplified your life, and you're working on a constant time slice. Within that constant time slice, you're looking for a codimension 1 surface, which is simply minimal area. Much easier to work with, okay, but less general, okay? And, yeah.
So the string theory we're used to geometry, infinite field, heat field, things like that. Is it possible this is just like a perfect approximation of the effects of flux?
So this is supposed to be exact within its, up to the order 1 corrections. So the order 1 corrections, in fact, let me just say, since I'm not going to have time to get to it, let me just say a word about the order 1 corrections, because they involve the other fields. So the order 1 corrections, according to work by Faulkner, Lefkowitz, and Maldacena, are roughly speaking the entanglement entropy of the bulk fields within R of A. So you look at within the bulk, so you sort of have some fixed background, and then you have quantum fields propagating on this background, and they have an entanglement entropy. And if you look at the entanglement entropy of R of A, and so that's all the bulk fields, whatever bulk fields you have, those give you the order 1 corrections. The order n squared part, the leading part, is supposed to only depend on the metric, and here what I'm talking about is the Einstein frame metric in particular. Yeah?
How do we think about the order 1 correction?
Right, so the order 1, so you have from the boundary point of view, you have a 1 over n expansion, I mean, essentially, as Oliver mentioned, when you're doing the large n limit, you're sort of doing a thermodynamic limit, and your extensive quantities go like n squared, and then your order 1 stuff represents statistical fluctuations. So from the point of view of the boundary, those are statistical fluctuations. Okay, so the main message I want to get across, and I don't have time, I've basically run out of time, so I'm not going to be able to go through this in any detail, but I mean, there are many, many things to be said about this formula. But in terms of what I did in the previous section, what I want to emphasize is essentially that this geometrizes all of these features of field theory entanglement. And so it's very beautiful because field theory entanglement is kind of this abstract thing. You try hard to calculate it, and then you get some answers. According to this, it's all properties of minimal surfaces. Okay, and so
You have 10 more minutes.
yeah, in terms of describing all of holographic entanglement entropy, that's still even 10 minutes is still okay.
I just didn't want you to think you were making it 5.
No, I understand. I understand that. So what is it geometrized? So ugh. So each of these was going to be like a whole section. The area law divergence pops out. So in particular, M of A, so in this case, A actually didn't itself have a boundary, but in this case, in this example, it does. And if A itself has a boundary, then M of A must meet the boundary of the space-time on the entangling surface. And if you look at how it meets it, it's going to meet it orthogonally because basically this thing is like infinitely far away. This boundary is infinitely far away, and then it should be pretty clear that you get this divergence, that this area is infinite, and furthermore, the infinity is proportional to the area of the entangling surface, and it depends if you can easily calculate how it depends on epsilon, and it comes out the right way. So that's fairly straightforward calculation. So this thing, area of dA over epsilon to the d minus 2, and then you can work harder and get subleading terms and get things like then you can also get in all of these, so ball entanglement entropy in CFTs, for which I gave formulas before, like C over 3 log L over epsilon, etc., with the F and the A in 2D and 3D. One thing I do want to say is that these examples are a total cheat, because if you want to think of them as checks on Ryu Takenagi, I mean, it's very nice how they geometrize this, but the way that they do it, see, as I told you before, the state of the vacuum is, in a CFT, is the thermofield double of the reduced density matrix in a ball. And the reduced density on a matrix on a ball is the thermal state on hyperbolic space. So, and that thing is represented holographically by a black hole. So this is actually just a special case, not of Ryu Takenagi, but of Bekenstein-Hawking. Okay, so in other words, these are all just black holes, really. And the same goes for the finite size, but let me just remind you of this plot for all these different cases, where we had the log L over epsilon, then we had the thermal case, and we had the finite size case, and we had the gapped finite size. This is just vacuum of CFT on the line, and this was thermal state. So you get all of these. In fact, it's a very nice, not difficult exercise to get these three from that formula. All three of these are cheats in this sense that they're all secretly just black holes in some funny coordinates. But let me still explain how it works out. When you have a thermal state, that's represented by a black hole. So let me do a thermal state on the line. And you have a black hole, and if your size, L, is small compared to basically the radial distance into the horizon, which is 1 over the temperature, then your minimal surface doesn't see it. So this is L much less than 1 over T. But if it's large, then what it does is it goes down and it hugs the horizon. And so you get this extensive thermal entropy from a piece of the minimal surface that hugs the horizon. So you get a little bit of Bekenstein-Hawking plus some entanglement, basically. And even though I said this is a cheat, it's only a cheat for basically balls, round balls in CFTs or in, but you can do this for any kind of geometry you want, and if the size of your region A is large compared to 1 over T, you pick up this extensive thermal entropy contribution. So again, this geometrizes that in a nice way. And then you could ask, well, what about the gapped system? And that's also beautifully geometrized. A gapped system is represented holographically, as I guess Oliver discussed, by having some kind of a cap on your radial direction. So now you have just some kind of a wall, and where your space ends. It's not a horizon, and in particular, it doesn't carry entropy. And now, if your region is small, and this basically is at a coordinate z, which is basically your correlation length. If your region is small compared to the correlation length, again, you're only sensitive to the UV part of the geometry, and you get that initial part of the curve. But what happens if it's large? So this is for L much less than the correlation length. If it's large, then the minimal surface just goes straight down here and down here. You don't count this part, which in any case, if the wall is from the compact dimension smoothly capping off, I mean, there's different walls you can construct, but then you actually see that in any case, the Einstein frame metric in this direction vanishes. So whether you include it or not doesn't matter. But morally speaking, you shouldn't include it because it doesn't carry entropy. Okay, and so you just get a constant, and so then it looks, what does it look like? It doesn't look exactly the way I drew it. It looks like this, and then there's a first order phase transition. So this was pointed out by Klebanov, Kutuzov, and Morgan, and it's quite an interesting behavior. You get a phase transition because you're in a large n limit. Okay. So even if you have, and this is in any dimension, so you have a finite size system and you wouldn't expect a phase transition, but because you're in a large n limit, you can have a phase transition. Okay, but so it geometrizes that saturation that we expected in a finite n system. It's a smooth crossover, but again, you get that saturation, and the reason geometrically for the saturation is that you just don't have, like, this stuff, morally speaking, this stuff in the middle is not entangled anymore with this stuff out here. This represents kind of entanglement of modes sufficiently close to the entangling surface, and then past the correlation length, there's no more entanglement. Okay? So it's really cool how it kind of realizes all of these examples. You can do the mutual information, and then you again get competing surfaces. You have two possibilities. It can look like this. So I'm trying to compute S of AB because I want to compute my mutual information. So M of AB can be the union of M of A and M of B. That's always one option. Or it can connect A to B. If this one is larger, if the yellow one is larger than the red one, then the red one is minimal. And then the mutual information vanishes. And this is what happens at large separation, because at large separation, the red one doesn't grow, but the yellow one grows. And so at large separation, so S large, it's 0, but here, well, if the separation is small enough that the yellow one wins, then you get a non-zero mutual information. So the mutual information looks like this. It looks very similar to what we had before, but it just hits 0, whereas before we had a smooth function that never hit 0. Now, doesn't this contradict what I said before, that it can't be 0, that if it's 0, then you have 0 correlators, whereas we know that in a holographic theory, we certainly have non-zero correlators? It's a question somebody asked me before. But of course, 0 means order 1. So it just says that, in fact, here, it's not really 0, it's order 1. And here, it's order n squared. And again, there's a phase transition, which is an artifact of the large n limit. Okay? And finally, what I want to say, so in fact, here, you see, it kind of follows from the fact that one option for the minimal surface is always the union. And the union has the area which is equal to S of A plus S of B. That means that so I just proved in words that S of AB can be no larger than S of A plus S of B. In other words, Ryu Takenagi knows subadditivity. And you can prove by a slightly more complicated argument that it knows strong subadditivity. So you can prove that it obeys this property just from simple manipulations of minimal surfaces. It's a very general proof. You have almost no ingredients in it, actually. It's almost disturbing how few. You need to know no holography or asymptotically ADS boundary conditions or anything like that to prove it. And you can also show, and this is, I think I'll end on this, you know that in a pure state, so one of the important things about entropy is that in a pure state, S of A equals S of A complement. And Ryu Takenagi knows that one too. I mean, this is a consequence of a Rocky-Lieb, which you can prove, but so this is just the fact that A and A complement in a pure state means there's no horizon, and therefore they have the same minimal surface. The other case is the more interesting one, and I promise I'll stop there. And this is an example of the application of the homology constraint, that in a mixed state this is not necessarily the case. So if you have a horizon, the horizon is an obstruction, is a topological obstruction as far as the homology constraint is concerned. And so it's no longer the case that they can share the same minimal surface. So I might have some minimal surface for A. Maybe it does something like that. This cannot be the minimal surface for A complement because this is not homologous to A complement. The thing which is homologous to A complement has to go around the horizon. So this would be, I should have used a different color. And therefore, they'll have different entropies. You can see in mixed states in general, A and A complement will have different entropies. And there's tons more to say, but I'm way over time, so I'm going to stop there. Yeah, that's one way to get it. Yeah, I mean, there's many ways. I mean, this gets to this top-down versus bottom-up thing. Sometimes people just put them in by hand. We just say space ends here. Or you can actually construct a solution to string theory that has a wall. Mm-hmm.
So, like, from the box point of view, like, I have, for arbitrary reading, I can have, like,
in the bulk, you mean?
Yeah, in the bulk.
Yeah.
Now, is that has any meaning
Probably, I mean, in principle, if it's well defined, so you would have to have some kind of diffeomorphism invariant way of specifying the region. And then if you have, then indeed it has an entanglement entropy. And so as a matter of principle, it means something in the theory, and therefore it means something in the field theory. But it's very unlikely to have like any sort of to have any simple meaning in the field theory. These regions which are bounded by minimal surfaces seem to be very special types of bulk regions.
Even for those regions, as I even calculated, for example, the box
Well, I mean, if you can tune n, then you can separate the two terms. I mean, it certainly has a meaning. You know, I agree that it's kind of getting swamped by the order n squared piece, but it's there. So, you know, if you have enough data, you could extract it, I suppose.
Continue with this discussion. Let's thank Matt again for this great set of lectures.
Thank you.